which is an abstract object, we'll call it $d. Formally, a graph is defined by two finite, non-empty sets. $, the set of
The
vertices,
dots.
the dots, exactly, or nodes, and a dollar, which is the set of edges.
The lines connecting them.
That's it.
Now, when we talk about a simple graph, which is what we'll mostly be dealing with, we have to impose two immediate rules, right?
Mm-hmm.
What are those constraints that make a graph simple?
Yes, and these constraints are crucial for theoretical analysis. First, edges are defined by unordered pairs of distinct vertices.
Okay, so that means no loops. An edge can't connect a vertex back to itself.
Correct. And second, there can only be one edge between any given pair of vertices.
No multiple edges.
Right. No multiple edges. This makes the structure unambiguous. If we remove these constraints, we get what are called multigraphs, but for most foundational study, we focus on simple graphs.
And if those connections have an implied flow, say the flow of traffic or information, we move into directional territory.
Exactly. When the edges have a required direction, like a one-way street, they're called arcs, and the structure becomes a directed graph or a digraph.
So in a digraph, the edge is an ordered pair.
Yeah,
It matters which way it's going.
it absolutely matters.
Okay, so once we've built our graph, we need ways to measure its scope. The source gives us immediate size metrics. First, there's the order, which is simply the total count of vertices.
And then the size is the total count of edges. These two numbers, the count of nodes and the count of connections, are, the most fundamental properties of any network.
Then we get more localized with the degree of a specific vertex. Let's call it dollars. This is just the number of edges connected to that vertex, how many connections it has.
Mhm.
But why do we bother with minimum and maximum degrees, delta G? And delta G, what do they tell us?
Minimum and maximum degrees, so delta and delta, tell you about the uniformity and the vulnerability of the network.
How so?
Well, if the minimum degree is very low, that node might be a weak point. If the maximum degree is very high, that node is a hub.
A potential bottleneck or a single point of failure?
Exactly. These are summary statistics that quickly convey the shape of the graph's connections.
Got it. Moving beyond simple counts, let's talk about neighborhoods. This seems critical for understanding immediate local structure. We have two key concepts here: the open neighborhood and the closed neighborhood. Can you contrast those clearly for us?
Certainly, the open neighborhood, which we write as MISA, is strictly the set of vertices that are adjacent to the Vel-Desirs neighbors.
So if you're at location, the dollars is every location you can reach in just one step.
Yes. Now, the closed neighborhood is the open neighborhood plus the vertex dollar itself.
That seems like such a small distinction, adding the vertex back into its own neighborhood. Why is that important?
It makes a world of difference in application. For example, if you are defining an independent set where no two chosen vertices are adjacent, you'd use the open neighborhood to define that rule.
Right, you'd say no vertex can be in the open neighborhood of another.
But if you're defining a dominating set, a set of vertices that either contains or is adjacent to every other vertex, you would rely on the closed neighborhood concept. The possibility of a node dominating itself is included.
So that subtle inclusion of dollar really changes the game.
Absolutely. Now we can transition from static structure to dynamic movement, connectivity. This is where we define how you actually move through the network, starting with the least constrained movement, the walk.
A walk is just any sequence of alternating vertices and edges. The key characteristic here is that a walk can repeat vertices and it can repeat edges, right?
That's right. It's the raw, unrestricted journey.
So you can go back and forth as much as you want.
You can. But then we progressively restrict the walk to gain more structural insight. If we insist on a walk with no repeated vertices, it becomes a path.
And paths are fundamental because the length of the shortest path defines the distance between 2 points.
Precisely. A path is the most efficient, non-redundant way to travel between two vertices.
And when a walk starts and ends at the same vertex, and that's the only repeated element, it forms a cycle.
Yes. Cycles introduce redundancy. They give you a way back to where you started without retracing your steps.
Okay, so based on this idea of a path, we can define a connected graph.
Right. If a path exists between every possible pair of vertices and dollars, the graph is connected. If even one pair lacks a path, the graph is disconnected.
And when a graph is disconnected, it breaks down into components. What are those exactly?
Components are the maximal connected subgraphs. It means you can't add any more vertices or edges to that component and still keep it internally connected. They are, the biggest possible internally linked chunks of the network.
I see. So since paths define distance, we can now establish metrics for centrality and dispersion. Let's start with eccentricity.
Eccentricity. Right. This is the longest, shortest path originating from a vertex dollar.
That sounds a bit like a paradox. The longest, shortest path.
It does, but let's break it down. Imagine you are running a server at vertex dollars. Its eccentricity tells you the worst-case time delay or latency required to send a message to any other node in the network.
So for my vertex dollars, I find the shortest path to every single other vertex. And then I pick the longest one of those.
Exactly. It's defined as the maximum distance from vi dollars to every other vertex stu dollars.
Okay, so eccentricity is a property of a single vertex, but it helps us define two essential global properties of the whole network, the radius and the diameter. How do we distinguish them?
The radius is the minimum eccentricity across all vertices in the graph.
So you find the eccentricity for every vertex, and the radius is the smallest one you find.
Yes. The vertices that achieve this minimum eccentricity are the central vertices, the ones that are, by definition, closest to the farthest points. If you want to place a central hub to minimize worst-case distance, you place it at a vertex with minimum eccentricity achieving the radius.
And the diameter, conversely, is the maximum eccentricity.
This is the absolute longest, shortest path that exists anywhere in the entire graph. If the radius tells you the best a network can be in terms of reach, the diameter tells you the bottleneck distance. It's the critical constraint on speed or reach.
That's a great way to put it.
And finally, related to cycles and distance, is girth. This is the length of the shortest cycle in the graph.
Girth.
Okay.
So why is this important?
Girth is essential for defining graph structure and sparseness. If a graph has no cycles at all, it's acyclic, like a tree. Its girth is defined as infinite.
So if a graph has a girth of 3, that means somewhere in the network there's a triangle. 3 vertices all mutually connected.
Correct.
And if the girth is 4, the smallest cycle is a square. Girth is a very precise structural fingerprint.
It is indeed.
Now we look at internal structural relationships, starting with containment. A subgraph dollar is simply a piece of the original graph dollar. Seems straightforward.
It is. But the spanning subgraph adds a crucial rule. It must include all the vertices of the original graph dollars, but it might have fewer edges.
So it's a structurally diminished version of D dollars, but
Yeah.
topologically complete in terms of nodes.
Yes. And this leads to the exceptionally important spanning tree. This is the maximal, most efficient structure we can extract, a spanning subgraph that is both connected and acyclic. It uses the minimum number of edges necessary to keep all vertices linked.
And we will get to why none one edges is the magic number for a tree very soon, I'm sure.
We will.
Okay, let's pivot to the concept of structural opposites with the graph complement.
For the complement, we use the exact same set of vertices, but we flip the edges. An edge exists in the complement dollar if and only if it did not exist in the original graph dollars.
And why is this a useful concept?
The complement is indispensable when studying concepts like independent sets and cliques. A clique is a subset of vertices where every vertex is connected to every other vertex in that subset. It's a complete subgraph.
And the clique number, omega g, is just the size of the largest clique you can find.
Right. And here's the connection. An independent set, a set of vertices with no internal edges, in D dollars is precisely a clique in the complement dollar.
Ah, so they're two sides of the same coin.
Exactly.
We also need to define chromatic number. This sounds practical.
Very. It's the minimum number of colors needed for a proper vertex coloring, meaning no two adjacent vertices share the same color. It's a measure of how complex the separation requirements are in your structure.
Like class scheduling. The chromatic number tells you the minimum number of time slots you need, so no two conflicting classes happen simultaneously.
Perfect example.
Okay, finally, before we hit the theorems, the source grounds us in the concept of the equivalence relation. This is a mathematical standard that has to satisfy 3 properties: reflexive, symmetric, and transitive. Why introduce this now?
Because we are about to use it to prove that two graphs being structurally identical, a relationship we call isomorphism, is a well-behaved formal equivalence relation, just like equality or congruence.
So we need to know that if graph G is isomorphic to H, then H must also be isomorphic to G.
Yes, it establishes the reliability of comparison. It's a foundational check.
Okay, we have the vocabulary. I think we're ready. Let's move into the immutable laws that govern these structures, the fundamental theorems that allow us to count, analyze, and characterize them.
Let's do it. We begin with the most famous counting result, the handshake theorem.
Also known as the first theorem of graph theory.
That's right. This theorem states that if you sum the degrees of all vertices in a graph, that total sum is exactly twice the number of edges.
The analogy is simple but powerful. If every edge is a handshake between two people or vertices, every handshake contributes 1 to the degree count of 2 different vertices.
Exactly. So when you total up all the individual degrees, you have counted every handshake, every edge, exactly twice.
And this simple theorem immediately leads to a foundational constraint called the parity result.
It does. Since the total sum of degrees must be even, because it equals 2 times the number of edges, this forces an intrinsic structural requirement on any graph.
Which is?
Every graph must have an even number of vertices with odd degree.
This is a requirement, not an option, and it's a fantastic example of mathematical necessity.
Yeah.
I mean, if you have an odd degree vertex, say degree 3, you're summing an odd number. To make the entire sum even, you must pair that odd degree up with another odd degree sum or another 2 and so on. The number of odd sum ends must be even.
This is a powerful, immediate test. If someone gives you a proposed degree sequence for a potential network, the first thing you check is whether the count of odd degrees is even. If it's odd,
You know instantly, without drawing a single line, that the proposed network cannot exist as a simple graph.
impossible.
And building on that, we have the special case for regular graphs, where every vertex has the same degree collars.
Right. If you have numbered vertices and each has degree tollers, the total degree sum is just 10 times another.
So the total number of edges must be exactly 10 into an array.
Yes. And this tells us, for example, that a graph with 7 vertices where every vertex has degree 3 cannot exist.
Because 7 times 3 is 21, and 21 divided by 2 is 10.5. You can't have half an edge.
You cannot.
Let's revisit walks and paths. It seems intuitive, but we need a formal theorem to state that if a walk exists between 2 vertices, a path must also exist.
We do. This theorem, which connects the conceptual ability to move, which is a walk, with the existence of the most efficient route, the path, is fundamental.
So how does the proof conceptually ensure that path exists?
The proof is an elegant exercise in simplification. If the walk repeats a vertex, let's say $6, it means that you traveled from $6 back to $6 along a cycle within the walk. You simply delete the section of the walk that forms that internal cycle. The resulting shorter sequence still connects your starting point and end point on Euler.
And you just keep doing that.
You repeat this process until no vertices are repeated, and you are guaranteed to find a path which will also be the shortest route.
We also discuss components, the maximal connected chunks of a graph. We have a theorem that puts a hard limit on how many components a graph can have based on its size.
Yes, a graph with no vertices and non-Euler edges must have at least no molar components.
Let's trace the logic there.
Okay, imagine you start with no vertices and 0 edges. You have no isolated components.
1 for each vertex.
Right. Now, for every edge dollar you add, you can reduce the component count by at most 1. That happens if the edge connects 2 previously separate components.
And if you add an edge within an existing component,
Then the count doesn't change, you're just forming a cycle.
so the best you can do is reduce the component count by 1 for each edge.
Exactly. Therefore, after dollar edges, the maximum reduction in components is Euler. Starting with dollar, you must be left with at least molar components. This is a powerful minimum bound, often used to check connectivity efficiency.
Right. Now we get to trees. These are the workhorses of graph theory, minimal, efficient, and essential for hierarchical structures. We already know a tree is a connected, acyclic graph, but the theorems surrounding them are arguably the most important foundational results.
Indeed. First, the spanning tree existence theorem. Every connected graph contains at least one spanning tree.
This is the constructive proof for why the minimal structure exists within the messy reality. Can you elaborate on that constructive proof? How do we guarantee finding that minimal structure?
The standard method is to start with your connected graph d dollars. If t dollars contains a cycle, you pick any edge from that cycle and remove it.
And removing an edge from a cycle never disconnects the graph.
Never. Because the rest of the cycle provides an alternate path. You just repeat this edge removal process until no cycles remain. What you are left with is a connected, acyclic subgraph that spans all the vertices, a spanning tree.
That structural efficiency, achieved by removing all redundant edges, leads directly to the core counting result for trees. A tree with Nama vertices has exactly Nala 1 edges.
That's the magic number.
That number, Nala 1, is the hallmark of non-redundant connection. How is that proven?
This is typically proven using induction focusing on the leaf structure. A tree with Euler greater than or equal to 2 vertices must always have at least 2 leaves vertices with degree 1.
Okay.
If you remove a leaf and its single incident edge, the remaining graph is still a tree, but with Nala 1 vertices and Nala 1 edges.
And by induction, you assume the smaller tree has NL1 edges.
Correct, which means our original tree must have had none edges. The logic holds.
Here's where it gets really interesting, the conceptual power of trees. The source lists 6 equivalent tree characterizations. For anyone studying this, mastering these equivalencies means you can prove a graph is a tree using structural properties, counting rules, or connectivity rules interchangeably.
Absolutely. Let's break these 6 properties into 3 high-impact pairings.
Okay, pairing 1, the definition and counting rules. The definition is 1, the dollars is connected and is cyclic.
And the counting rules are 2, $dollars is connected and has none edges, and $3 is a cyclic and has none edges.
So this means if you confirm either connectivity or R is cyclicity, simply counting the edges to be on a 1 confirms it's a tree.
Yes, it's a huge shortcut.
Okay, pairing 2, the path and cycle rules.
Right. Number 4 is, there is exactly one path between every pair of vertices. This is the direct result of connectivity without redundancy. If there were 0 paths, it wouldn't be connected. If there were 2.
They would enclose a cycle. Makes sense.
And this is strongly linked to number 5. $dollars is a cyclic, but adding any new edge creates exactly one cycle.
So this defines the tree as being on the absolute cusp of forming redundancy. It's maximally acyclic.
Perfectly put.
And finally, pairing 3, the connectivity bridge rule.
This is number 6. The dollars is connected but loses connectivity upon any edge removal.
And this is the key structural insight. Every edge in a tree is a bridge. If you remove any single connection, the network splits.
It does. This confirms the total lack of redundancy we found with Yiddy dollar edges.
The fact that these 6 seemingly different statements about paths, cycles, edge counts, and connectivity are all mathematically interchangeable is what makes the tree structure so powerful in mathematics.
It truly is.
We shift now to structures defined by specific functional constraints. We'll start with Eulerian graphs, a concept that originates from Leonhard Euler solving the famous Königsberg Bridge problem back in the 1730s.
Yes. Euler was trying to determine if it was possible to find a continuous walk that crossed every single bridge exactly once and ended where it began.
And in graph theory terms, he was looking for an Eulerian circuit, a closed trail that uses every edge exactly once.
Right. An Eulerian path is similar. It uses every edge exactly once, but doesn't necessarily close.
The genius of Euler was realizing this boiled down entirely to the degrees of the vertices. The Eulerian circuit characterization states that a connected graph dollar has an Eulerian circuit if and only if every vertex has an even degree.
We call that an even graph.
And the proof is highly intuitive, isn't it? It relies on parity.
It does. For a circuit, every time you arrive at a vertex, you must immediately have an edge available to leave that vertex. Arrival and departure?
The edges have to come in pairs.
They have to, which makes the total degree even. If a single vertex had an odd degree, say 5, you could enter it twice and leave it twice, but the 5th edge would leave you stuck there, unable to return to your starting point to close the circuit.
But not all problems require ending where you started. What if we just need to traverse everything once? That's where the Eulerian path characterization comes in.
This theorem states that a connected graph dollar has an Eulerian path if and only it has exactly 0 or 2 vertices of odd degree.
0 odd vertices, of course, means it's a circuit.
Right, that's the base case.
So if there are exactly 2 vertices of odd degree, say 2 and dollars, where must the path start and end?
They must be the start and end points of the path. The formal proof illustrates this perfectly. If you add a temporary edge between $2 this raises both their degrees by 1, making all vertices even.
So you've just created a Eulerian circuit on a slightly modified graph.
You have. Then, if you remove that temporary edge, the circuit breaks, starting at $2 and ending at $1, or vice versa, using every original edge exactly once.
These 2 theorems are essential for real-world route optimization, like mail delivery routes or snowplow routes, where efficiency requires covering every road once.
Absolutely. Furthermore, the structural consistency of even graphs leads to the even graph decomposition theorem.
Decomposition sounds complex. What does that mean in practical terms?
It means you can break the entire set of edges into smaller, independent loops that don't share any common edges. The proof works recursively. Since every degree is even, the graph must contain a cycle. You find one cycle, you remove its edges.
And the remaining graph still has all even degrees.
It does, so you just repeat the process. Eventually, the entire graph is gone, decomposed into its constituent cycles.
And as a final note on Eulerian structure, we have the theorem that in an even graph, every maximal trail, a trail that cannot be extended further, must be closed.
Yes, if you start walking in an even graph, you simply cannot get stuck in the middle of a route. You must always be able to return to a previously visited vertex, ultimately closing the circuit.
You can't get stranded.
You can't.
Let's shift to bipartite graphs. These are graphs where the vertices can be partitioned into two distinct, independent sets, say $6.
And all edges run between $6. There are no edges within $6 or within $.
Bipartite graphs model relationship structures perfectly like workers to tasks or people to the languages they speak. The sets are defined by a specific binary property.
And here's where it gets really interesting. The bipartite characterization theorem provides a necessary and sufficient condition for a graph to be bipartite. A graph is bipartite if and only if it has no odd cycles.
This is a cornerstone theorem, linking an algebraic property, the partition, with a geometric property, the cycle length. So why do odd cycles prevent bipartiteness?
Well, let's trace the contradiction. If a graph is bipartite, imagine you start in set $6. Any movement, one edge, takes you to dollars.
The next edge takes you back to $6.
Right. The length of any path must alternate between 6 and the dollars. Therefore, any closed walk a cycle must have an even length to get you back to your starting set.
So if a cycle had an odd length, say 5 edges, you would start in $6, take 5 steps, and end up in dollars. But since it's a cycle, you must end back where you started in $6.
That's the contradiction. It proves that no odd cycles can exist in a bipartite graph.
And the reverse proof, showing that if there are no odd cycles, the graph must be bipartite. Uses distance, right?
Precisely. If we assume no odd cycles exist, we can take an arbitrary starting vertex U. We define set $6 as all vertices at an even distance from U, and set $$ at an odd distance from $.
Okay, so you've created a partition based on distance.
Yes, and if two vertices in $6 were adjacent, their distance from UDAL would both be even, say 2KL110 and 2KL22. The two shortest paths from $1 to those vertices, plus the edge between them, would complete a cycle.
And the length would be something like 2KL11 plus 2KL2 plus that one extra edge.
Which is an odd number. Since we established that an edge between two vertices of the same parity creates an odd cycle, the assumption of no odd cycles forces the distance-based partition to be valid. This is one of the most conceptually rewarding proofs in graph theory.
Wow. Finally, we have a simple counting rule for regular bipartite graphs. If the values of scale are regular, meaning every vertex has degree dollars and it's bipartite, with partitions 2 and dollars, then the two partite sets must have equal size.
Yes, dollar must equal dollar, and this follows directly from the handshake theorem.
Let me guess. You count the edges from both sides.
That's it. Every edge connects a vertex in no dollar to a vertex in no dollars. If we count the edges originating from $2, we get 2 times $0. If we count the edges incident to dollars, we get 2 times $1.
And since the total number of edges is the same,
The dollar must equal dollars, which forces the sizes to be equal.
now we step into the tools needed for computation and deep structural analysis. If we want to hand a graph off to a computer for processing, we need formal matrix representation.
Yes. The most common representation is the adjacency matrix. For a graph with no vertices, $0 is a null to non matrix. The entry ODO is no dollar if there's an edge between 5U$ and V$ and dollars otherwise.
For simple graphs, the matrix dollar has several immediate properties. It's symmetric, meaning AG equals AG, since the connections are mutual. And it has zeros on the main diagonal because we exclude loops. We also know that if you sum up the entries in any given row dollars, that sum gives you the degree of vertex.dollar.
All correct. But the truly critical application comes when we start using linear algebra. The theorem states that if you take the Taft-Thayer power of the adjacency matrix, the entry gives you the exact number of walks of length k from vertex Euler to 5 Eulers.
This is a revolutionary tool for network analysis. If I want to know how many possible communication paths of exactly 5 hops exist between my server and a client, I don't choice them manually. I compute Fayvadius $5 and just read the entry.
You do. The proof relies on the definition of matrix multiplication. When you compute A tau 2, the entry sums up the product area R over all intermediate vertices dollars.
Which is basically counting all the two-step paths.
It correctly counts all walks of length too. And induction extends this logic to any length dollars.
It's important to distinguish this from the incidence matrix. Euler, how is that different?
The incidence matrix is 1 times Euler, so vertices versus edges. The entry Euler is a 1 if vertex Euler is incident to edge A, and dollars otherwise.
So it's better for tracking edge utilization in flow problems.
Exactly, whereas the adjacency matrix is superior for tracking connectivity and distance relationships.
Okay, how do we know if two networks are fundamentally the same? Even if one is drawn differently or uses different labels, that takes us back to graph isomorphism.
Two graphs, the dollar and dollars, are isomorphic if you can find a perfect one-to-one mapping of bijection between their vertex sets that preserves adjacency.
So if two vertices are connected in G, their corresponding partners must be connected in H, and vice versa. They are structurally identical.
Precisely.
And as we lay the groundwork for, the theorem confirms that graph isomorphism is, in fact, an equivalence relation.
It satisfies the three requirements. It's reflexive. A graph is always isomorphic to itself. It's symmetric. If G is isomorphic to H, then H is isomorphic to G. And it's transitive.
If G is ln H and DOA con K, then they'll ln K.
This formal classification makes isomorphism a rigorous tool for classifying graphs.
This leads directly to the complement isomorphism theorem. If two graphs are isomorphic, their complements are also isomorphic.
That's right. If $2 is structurally the same as dollars, then the set of missing edges in no dollars must also be structurally the same as the set of missing edges in the dollars.
The structural preservation applies to both the connections that exist and the connections that don't.
Exactly.
And we get interesting special cases here, like the self-complementary graph, where a graph is isomorphic to its own complement.
It means the structure of the connections is exactly the same as the structure of the non-connections. Very
graph onto itself, so it's a formal way of talking about symmetry within a single graph.
Yes, like rotational or reflectional symmetry. If a graph has many automorphisms, it has high structural symmetry.
Let's return to our distance metrics. Radius and diameter. We have a theorem that sets a strict relationship between them.
For any connected graph, the diameter is bounded by the radius. Specifically, radicität, the G Ledium Radok.
The first part is trivial. Minimum eccentricity is always less than or equal to maximum eccentricity. The upper bound is a powerful constraint.
It is. The proof relies on locating a central vertex, $2, one that achieves the minimum eccentricity, the radius.
So we pick $2. Now take any two vertices and ballers that define the diameter. They are the two furthest points in the network.
Right. The shortest path between sum and dollars, which defines the diameter distance d, cannot possibly be longer than the path that goes from third to dollars and then from sec to the dollars.
The triangle inequality.
Essentially. Since $C is a central vertex, the distance from 6 to 6 is at most the radius. Similarly, the distance from 7 to dollars is also at most the radius.
So the distance between U and V has to be less than or equal to radius plus radius.
Which is 2 times the radius. This caps the maximum path length at twice the optimal center path.
That's a huge constraint for network design. If you know the best case global latency, the radius, the absolute worst case latency, the diameter, cannot be more than double that.
It's a very useful bound.
Okay, the final key tool in this section addresses the reverse problem of the handshake theorem. Given a sequence of potential degrees, is it actually possible to draw a simple graph that satisfies them?
This is the Hubble-Hakimi theorem. It determines if a sequence is a graphic sequence.
This sounds like a necessary check before building any large network model.
It is. The theorem provides a recursive test. If you have a non-increasing sequence of degrees, say dollars, you take the largest degree, D1.
Okay.
The theorem states that dollars is graphic if and only if the modified sequence, the dollars, is graphic, and the nuller is what you get by removing $1s and subtracting 1 from the next largest remaining degrees.
Let's make that conceptual. If the largest degree is 4, that means that vertex must connect to 4 other vertices. The recursive test essentially assumes that those 4 connections happen to the next 4 highest degree available vertices.
Exactly. The logic is that if a graph exists, you can always rearrange the connections so that the highest degree vertex is connected to the vertices that need the most connections. If the modified smaller sequence is graphic, you can re-add the vertex and its connections, proving the original is graphic.
And you just repeat this process.
You repeat it until you reach a sequence of all zeros, which is trivially graphic, or until you get a sequence with negative entries, which is impossible. That proves whether the original network is mathematically possible.
We end this analysis section by considering vulnerability. We previously defined the bridge and the cut vertex.
Right, an edge whose removal disconnects the graph, and a vertex whose removal disconnects the graph.
The theorem governing removal, Theorem 2.21, quantifies the damage. First, removing a vertex after of degree dollars results in at most dollar components, y at most d.
Because the edges connected to the dollars are now gone. These dollar neighbors of dollars are isolated from each other unless they had alternative paths connecting them that didn't go through dollars.
So in the worst case, if the d neighbors were only connected through v,
removing dollars would create separate components, one for each neighbor.
And the second part of the theorem gives us the guaranteed result for edge removal. Removing a bridge yields exactly two components.
This is a direct consequence of the definition. If a graph is connected and an edge is a bridge, that means the edge was the sole connection between two large blocks of vertices. Removing it guarantees that those two blocks become independent components.
Making the total count exactly two. This confirms the extreme vulnerability associated with bridges.
It does.
Our final section delves into the specialized world of directed graphs and concludes with two essential advanced theorems in coloring and matching.
Okay. When dealing with digraphs, our simple degree concept splits into two parts. We have out degree plus V, the number of arcs leaving dollars, and in degree, the number of arcs entering dollars.
And just as we have the handshake theorem for undirected graphs, we have the directed handshake theorem.
Yes. This one states that the sum of all out degrees equals the sum of all in degrees, and both sums equal the total number of arcs.
Because every single arc has a start point and an end point. It contributes exactly 1 to an out degree count and exactly 1 to an in degree count.
Correct. This ensures the total input activity equals the total output activity across the whole network.
We mentioned that assigning a direction to every edge of an undirected graph is called an orientation. A highly specialized orientation is a tournament.
A tournament is an orientation of a complete graph. Since every pair of vertices in a complete graph is connected, in a tournament, every pair of vertices has exactly one arc between them.
Think of it as the result of a sports league where every team plays every other team exactly once and there are no ties. The arc dictates the winner and loser.
A perfect analogy.
A more advanced structural concept in digraphs is the kernel. This requires two properties. A subset of vertices dollars must be independent and dominating.
Right. Independent means no arcs within dollars, and dominating means every vertex outside dollars has an outgoing arc to some vertex in dollars.
So the kernel is a set of stable sources or dominant points.
It is. And the kernel existence theorem states that every digraph with no odd directed cycles has a kernel. This is a very complex condition, often linking the structural properties of odd cycles to the ability to define a stable, non-conflicting core set within the network.
We conclude our deep dive into the source material with two highly famous and applicable theorems, starting with the five-color theorem for planar graphs.
A planar graph is one that can be drawn on a flat surface without any edges crossing. The theorem states that every planar graph can be properly colored using at most 5 colors.
We often hear about the four-color theorem, which states that 4 colors suffice to color any map. But why focus on the five-color theorem here?
The 5-color theorem is far more fundamental for students because its proof is relatively straightforward. It relies on an essential structural property of planar graphs. Every planar graph must contain at least one vertex of degree 5 or less.
So the proof uses induction on the number of vertices. If you find that low-degree vertex, $, you remove it. The remaining graph is 5-colorable by induction.
Exactly. When you put vitals back, since it had at most 5 neighbors, those neighbors can use at most 5 different colors.
And since you have 5 colors to work with, even in the worst case where all 5 neighbors have different colors, you can.
Oh, wait.
You've spotted the subtlety. If the
Yeah.
5 neighbors use 5 different colors, you're stuck.
Right.
But the proof has a clever trick called a Kempe chain argument, which shows you can always swap some colors around to free one up for your vertex dollars. So you are always guaranteed to find a permissible color among the 5.
And finally, perhaps the most important application theorem, essential for logistics, scheduling, and operations research, Hall's marriage theorem.
This provides the necessary and sufficient condition for finding a complete matching in a bipartite graph.
A complete matching here means that every vertex in one of the partition sets, say $6, is paired uniquely with a vertex in the other set, $.
Yes. Hall's theorem states that a matching covering $6 exists if and only if, for every subset, $6, the size of its neighborhood, is greater than or equal to the size of dollars itself. So thought for job. Let's call this the collective dating rule. If $6 is the set of employees and dollars is the set of available tasks, and an edge means an employee is qualified for a task. If I take any group of 3 employees, those 3 employees must collectively be qualified for at least 3 different tasks.
That's the key insight. The condition must hold for every possible subset $6. If you find even one group of employees where the number of tasks they are collectively qualified for is smaller than the size of their group, then the matching fails. A complete matching is impossible.
That's the necessary part of the condition. But what makes Hall's theorem profound is that this local numerical check is also sufficient.
Yes. If you prove that every single subset satisfies this inequality, you are mathematically guaranteed that a complete pairing exists. This moves from necessity to certitude.
That was an exhaustive and highly rewarding deep dive. We started with the minimalist definition of the graph itself, moved through the necessary arithmetic of a handshake theorem, mastered the structural efficiency of trees, and arrived at the high-impact theorems governing connectivity and allocation.
What stands out here is how consistently the fundamental definitions are used to build increasingly powerful theorems. The simplicity of the degree count immediately dictates parity requirements.
And the existence of an odd cycle immediately invalidates the bipartite property.
Exactly. Use the logical flow of these definitions leading to their corresponding theorems as your study framework.
We covered essential study points, from contrasting radius and diameter to understanding how adjacent